In my previous couple of videos, I explained simple harmonic motion and the equations that can be used to describe it. In this video, I wanted to discuss pendulum motion. The simplest pendulum consists of a string with a small mass attached to it. While this system is at equilibrium if the string hangs vertically, if the mass is raised to a certain point, it will oscillate back and forth continuously. While studying ideal pendulum motion, we typically neglect the mass of the string and say that the only mass exists in the object attached to it. We also neglect friction so that we can say it will oscillate indefinitely and never slow down. This might seem like simple harmonic motion since the mass will oscillate continuously with an equal amplitude on either side of the equilibrium position. Much like in simple harmonic motion, the speed of the pendulum bob is momentarily zero at its amplitude, and the speed is greatest at the equilibrium position. You might remember from my other videos that simple harmonic motion exists when the restoring force is proportional to the displacement. This is the force necessary to bring the system back to its equilibrium position. To understand how pendulum motion is different from simple harmonic motion, it's important to understand the quantities used to describe pendulum motion. The first quantity you'll need to understand is the maximum displacement. This is simply the arc length from the equilibrium position to the pendulum bob at its amplitude. We know that an arc length can be found by multiplying a radius with the angle between 2 points on that arc. Here, that radius is just the length of the string, and the angle is the angle between the string at its equilibrium position and the string at its amplitude. It's important to realize that the angle measurement must be in radians. Also, know that these quantities are equivalent on the other side of the equilibrium position. We can say that pendulum motion is only simple harmonic motion if the restoring force is proportional to theta. To find out if this is true, we'll need to solve for the restoring force. We know that the pendulum bob has a weight that acts downwards, so the restoring force will be the component of this weight that acts tangent to the displacement arc. This is simply the weight of the pendulum bob multiplied by the sine of theta. We can call the restoring force F and say that F is equal to the negative of the mass multiplied by the acceleration due to gravity, multiplied by the sine of theta. We add the negative sign here to say that the restoring force acts in the direction opposite to the angular displacement. Similarly, we also saw this negative sign added when finding the restoring force in simple harmonic motion. This formula is actually all that we need to see that this is not simple harmonic motion. Here we see that the restoring force is proportional to the sine of theta and not to theta itself. However, it's actually very common to model pendulum motion as simple harmonic motion. As the value of theta decreases, the value of sine theta can be more accurately approximated by just replacing it with theta. This can be observed by looking at the diagram and noting how the displacement arc length becomes closer to the length of L sine theta as theta decreases. For small angles, we can therefore approximate the restoring force as the negative of the mass multiplied by the acceleration due to gravity multiplied by theta. From the arc length formula, we know that theta is equal to the arc length divided by the length of the string. We can substitute this in for theta to find that the restoring force can be approximated by the negative of the mass multiplied by the acceleration due to gravity divided by the length of the string multiplied by the displacement. Note how this equation closely resembles Hooke's law. In Hooke's law, force is equal to the negative of a force constant multiplied by a displacement. For pendulum motion, the effective force constant can be written as the mass multiplied by the acceleration due to gravity divided by the length of the string. Using these formulas allows us to approximate pendulum motion as simple harmonic motion, with a restoring force proportional to the displacement. Doing this allows us to use the formulas that we previously found for simple harmonic motion to describe pendulum motion. For example, in simple harmonic motion, we were able to calculate the period using the following formula. Substituting in the force constant that we approximated and simplifying, we can find that the period for a pendulum is equal to 2 pi multiplied by the square root of the length of the string divided by the acceleration due to gravity. Because the frequency is just the reciprocal of the period, we can also find that the frequency is equal to 1 over 2 pi multiplied by the square root of the acceleration due to gravity divided by the length of the string. We now have two useful equations for describing the motion of a pendulum. Keep in mind that these are still approximations and they'll be most accurate when theta is smaller. You might have noticed that the mass of the pendulum bob doesn't appear in either one of these equations. This is in contrast to simple harmonic motion, where a larger mass increases the period and decreases the frequency. We can also see from these equations that there's no dependency on the amplitude of the pendulum. However, this isn't exactly true. This is only a result of assuming that theta is a small value. Unlike in simple harmonic motion, in pendulum motion, as the amplitude increases, it will have a greater effect on the period. I hope that this video was helpful in explaining the difference between simple harmonic motion and pendulum motion. While pendulum motion is somewhat different from simple harmonic motion, we're able to use equations that approximate it as simple harmonic motion when the values of theta are low. If you still have more questions on this topic, feel free to comment below or visit fastphysicshelp.com for more information. If you found this video helpful, please give it a like and consider subscribing to the channel for more fast physics videos. Thanks for watching.